So in this lecture, we will study about the Poynting theorem and power flow. So when you have electric and magnetic fields which are varying with time or they are propagating in the space, they will carry the power with them and they are flow in particular direction. The power will flow from EM waves in some direction. So we will study the how the energy is flowing with the EM fields and what is the Poynting theorem and how we can interpret it. So we will again use the Maxwell's equations to get some expressions or equations, and then we will try to understand the Poynting theorem with respect to those equations. So let we have these equations. You can go through them, and using these Maxwell's equation, we can modify these one using some applying some theorems, dot products, or the cross products. So ultimately, when you proceed this derivation, you will get this expression here, this one. So this is more important. So I'm skipping the derivations. You can directly go through those derivations, and you will see here. So you can go through these starting from this point. You can go through these equations. Here we have this one. And then finally we get this one. So we will try to understand this expression, these equations. So we have now the closed integral of E cross H dot ds equals to minus del over del t integral over the volume for this half epsilon E square plus half mu H square dv minus this V sigma E square dv. So let's assume that to understand this step by step, make it simple. So we let assume that the dielectric or the medium is lossless. So for the lossless mediums, sigma will become zero. So for this time, let's assume first that this part will become zero because sigma will be zero for the lossless. So for the lossless medium, what we have this equation is remain. This term will be zero. Now we know that if you have an electric field and the magnetic field in certain volume, then this part will give you half epsilon E square will give you this energy associated with the electric field, whereas this part will give you the energy density associated with the magnetic field. So these are the energy densities associated with the electric field and the magnetic field, and you integrate with certain volume V. If you have some volume, and then you have the electric field, magnetic field inside this volume, they will have some densities with them. Then this will be a total uh, energy density with the electric and magnetic fields, and then you integrate with this volume, you will get the total energy. So this will be the total energy. So this part will be the total energy within a volume due to the electric field and the magnetic fields. Now this is a del over del t. This is a rate of change of this energy that will give you the power. So this term will become the rate of decrease in energy stored in electric and magnetic field. If you have some certain volume, so they will have some energy. So this factor, whole factor will give you the how the energy is changing, decreasing within that volume with the time. So it is the rate of decrease of the total energy. So this term will give you the how much energy is decreasing with time in that particular volume. So this is the rate of decrease of the power within that. So this is zero. So it means this expression E cross H dot ds over closed integral over this closed surface will give you the how much power is decreased inside the volume. So the same amount of power which is decreased in the volume, which it means that amount will come out from that volume because energy cannot be created or destroyed. So always it can be transferred. So it means if you have some volume and energy is decreasing, the power is decreasing here, it means that decrease in power is coming out from this volume. That's why it is decreasing. So it means this factor will give you the power which is coming out from this volume. That is the total power leaving the volume due to this factor. So this now if you have the lossy dielectric, the lossy medium, that will have some conductivity. In that case, due to that conductivity, we have the flow of current, and due to the flow of conduction current, you will have some ohmic power losses in that medium. So this expression will give you the this power per unit volume lost in that particular volume. How you can just compute that? If you have, let me open this whiteboard. Let me stop it here, pause the video, then I will again when it is open. So let's see here what we have. So we know that J is given by sigma E square. That J and E are the vectors. So we know that. Now multiply J with E. What you will have? Sigma E square. Now what is this sum? This is current I divided by per unit area, that is the current density, and here we can write E as a V, voltage over some distance, the distance. So if you want to find the electric field, just in simple we have V over D, and which is here sigma E square. So here you will have I V over certain volume. This is a V is a voltage, and this V is the some volume. So is the area, per unit area, and this is the per unit distance. So this quantity is same as sigma E square. And what is this? We know that this is the IV is the power lost in the medium where the current is flowing having a certain voltage V. So you already know IV is the power loss, and this is a per unit volume. So it is the power loss per unit volume. So this is the power per unit volume loss in the medium, this one. This is the power density which is lost due to some conductivity. So when you integrate this one over that volume, that will give you the total power lost in the medium in volume V. Okay. So when you have the lossy medium, then you have also the ohmic losses. Then this total power will be now equals to the rate of decrease in the energy stored in the electric field minus the ohmic power dissipated. So this is how. So if you compute E cross H, if you have electric field and magnetic field and you take the cross product and then you integrate over this closed surface ds, then that will give you the total power leaving the volume. That is the power which is decreased in associated with the electromagnetic field in the given volume, and the power which is lost in the medium. So this Poynting theorem states that the net power flowing out of a given volume V is equal to the time rate of decrease in the energy stored within the volume V minus the ohmic losses. Okay, this is the point. So this theorem is the Poynting theorem, which is stated by this equation. So therefore, rate of flow of energy outward through the surface and close the volumes V. So what we can say now? So here you have some certain volume. So total the power which is coming out to this volume V, which is flowing out from this volume and everywhere, this is given by this expression. This is here. So if you just know electric field magnetic field and you take this expression, if you take the cross product and then you integrate with this surface over this surface, then you will get the total power which is coming out from you. It means this is a power density because you are taking dot product of the ds. So this is the total power per unit. This so total power here given by this integral. So here you have this is ds. So here this will be some power per unit area. This is a power per unit area, per unit surface, and so on. So we because E cross H is a vector, so we give this special name. It's called this vector is called the Poynting vector. P dot ds. So we replace E cross H with the P, and P is called the Poynting vector, and this is P equals to E cross H is known as the Poynting vector. And because this is a power density, so the unit will be watts per meter. So it will give you the power density associated with E and H at that particular time. So now we know that E for the uniform plane wave, E and H are perpendicular to each other, and if you take E cross H, the vector, this vector will give you the direction in which the wave is propagating. It means the Poynting vector has the same direction in the at the direction of the wave propagation. So if you have the electric field and magnetic field and they are moving in a space, you have a wave moving in this direction. So and you have some this electric field in this direction and the magnetic field for perpendicular to this one. So here with this one, this electric field and magnetic field will give you power at this point, and which the power is flowing in this direction of propagation. That is the energy. The power is scalar quantity, but you can say that this power is associated with electromagnetic field and which is flowing in this direction. As the E and H also moving in this direction, so it means with this power density will also be moving in the same direction. So E cross H will give you the power density of this one. So and the direction of P will give you the direction of the propagation. So the Poynting vector is a measure of rate of energy flow per unit area at that point. This is because E and H is a function of time and space. So at particular point in the space, this E and H will become a function of time. So Poynting vector is a function of time as well. So it is called the instantaneous power density. It will this Poynting vector P will give you the instantaneous power. So whenever you want to find the power density, instantaneous power density, just we take the E cross H and you will get the power density which is flowing in particular direction. So for the uniform plane wave, the direction of wave propagation is this one. We already know. So the Poynting vector is the direction of points along AK. The flow of power is along the direction of wave propagation. So what we have some figures to see that. So here, for example, if these the electric field and the magnetic fields propagating in the space, so this vector will be the Poynting vector S. So sometimes denote with the P, sometimes denote in the S. So here they have shown in this. We had taken some website that is here given is this address. So we can understand from this figure that this is the direction of the propagation also, and this vector will also give you the Poynting vector direction. And the magnitude of this Poynting vector will give you the power density at that point. Okay. And here I have another animation, which is I have taken from the Wikipedia, that we have some antenna where we have a special antenna, dipole antenna. You will study later classes in the next course. So it is generating some EM fields, though they are not exactly uniform plane wave. Well, where you move in the far space, you can approximate to the uniform plane waves. They are wavefront now approaching to the plane front. So here the EM field generating and each the fields are moving in the space. So here it is moving in this direction. So for E and H fields, this point we have some Poynting vector which is moving in the particular direction. So these vectors are giving the direction of this Poynting vector here. As you move outward, this density is decreasing because total power remains same. If you find out the power density at this point, then it will go decreasing as you proceed outward. So this is how the wave is propagating for this dipole antenna, and the Poynting vector is moving particular direction. This Poynting vector gives you the energy density at this particular point. So now we will compute for a particular case. So we have in a lossy dielectric, E and H field for the uniform plane wave is given by this expression. Now we have taken the direction of propagation to be Z. Previously we have taken the direction of propagation to be X, now just taken Z here. So the electric field will be perpendicular to this direction. Either it will be in the Y direction or on the X direction or in the XY plane. So for simplicity, we take just the direction of the X axis. So we have AX component here, and this is the magnitude, P magnitude, and it will alpha Z will give you the attenuation factor, how fast it is attenuating as it moving in the space. Then if you know the EX, you can find the HY. So HY, the direction of this HY is this will be perpendicular to the Z and X both, and you can compute this one AH will be just the direction of this one will be the this one AK cross AE. So now what you calculate, this is a Z, this is Z, AZ cross AX will give you the AY. So the direction will be AY, these two remain same. Now HOY you can compute just dividing this one with one. So if you find out actual expression, so here you will have this one. So we have already found that. Now due to this lossiness, this wave, this will be out of phase by theta and amount, and it will be divided by the eta, absolute value of eta. Now we want to find out the Poynting vector of these two fields. So Poynting vector you can compute Ex cross Hy, because we have only x component y, so you can go through Ex cross Hy. So when you solve this, so you are getting this one. So now as this is E and H are depending on the time, so this Pz, there is a Poynting vector which is pointing in the z direction, because will be direction proportion in the z, so P is have the direction in the z axis, so we can say this is the Pz component. So Pz will be E of x over 2 eta e2 minus 2 alpha z cos 2 omega t minus 2 beta z minus theta n. So, and this is the expression we obtained for the uniform plane wave, where E and H are perpendicular and have a direction AX and AY. So now what we can say, now the power will be attenuating. It is moving in the Z direction. This power will also attenuate with as you move in the space by this factor 2 to the power minus e to the power minus 2 alpha z. These all are remaining constant. So the power will also decrease and move into the space, because E and H both will decrease, the magnitude will decrease, so the power will also decrease. Now the rate of decrease is twice of that of the E and H, because we have minus 2 alpha z. So we can understand easily because we have E into H. So now the decrease will be faster, rate will be faster for the power. So here we have the obtain the expression of the Poynting vector for the for instantaneous time for each time. So you can find for, so depending upon the space which point you are locating, that is if you propagate in z-axis, so particular z, what is the Poynting vector and particular time, the particular time and z we can know. Now because if you want to compute the this Poynting vector for particular point, then we have this will give you also the for the particular time. So it is not very useful term to find this one. Rather we talk about the average time average Poynting vector, which is more commonly used and used to find different values of power density. So we want to find the power density at particular point. So rather of this instantaneous power density, we'll talk about the time average. So since we are dealing with a sinusoidal signal, the time average Poynting vector or time average power density is a quantity that is more practical value and will be. So what is time average? Just you take average over one time period. So here you have the omega, which have the time omega equals 2 pi over t. So over that particular t, we will average this one, will give the time average. That will become independent of the time, and you can say this is the average power density at particular point in the space. So you can denote with this is the this two brackets p, and here you can also call the p average z. So here this is all a vector quantity, because Poynting vector we denote with a vector quantity. So here this you can compute by taking the average of this t at this one. So when you find out this time average Poynting vector, this is called the time average Poynting vector. So when you compute here, so you open this one expression. So now you have this is 2wt. So you have scaled by this cos by 2. So the time period will be half of this one. So means that at t by 2, t by 2, this will start repeating. So it means you have two cycles and in t duration. So when you take the time average of this, it will becomes out to be 0. This vector will automatically 0, because you have two cycles in to average over this one. So you have now two cycles will be there. So when you average these two cycles, the positive and negative, it will be cancelled out. Only term remain the cos theta n. So when you integrate, it will be independent to t. So it will be t, and then you have the average by t, so it will be cancelled out. You will get this one. So this is the time average Poynting vector, which is a function of z. So as if you increase the value of z, this this uh, time average Poynting vector will decrease. So it depend upon this eox 2 eta e to the minus 2 alpha z cos theta n. So this is very important quantity, and then will be used in the later lectures also for solving the questions, and in the higher courses also. Whenever you want to find the power density of EM waves, then we will always use the Poynting vector. So either we can find the instantaneous uh, Poynting vector, or generally we more oftenly use a time average Poynting vector. So this is the expression we will use to find the average power density at particular point in the space. Now, second thing is that this is a for the general case for the lossy dielectric. If the dielectric is lossless, in that case theta n will become 0 because eta will become real. Theta n will become 0, it will vanish, and you will have to, so pz will become this. Pz will become eox by twice eta. Eta is a real quantity, and now alpha will also become 0 as with lossless. So attenuation will be 0, and this term will become 1. So you will have just eox over 2 eta for the lossless dielectric, or in the free space also, because free space is a very good dielectric, and there the conductivity is 0. So in this case also, in the free space, generally we are dealing with the EM waves in the free space. So because in general we have the communication channel to be the free space in the wireless, for example, wireless channels and others. So in that case, we will use the time average power density to be e to the eox square by 2 eta generally. So once we know this magnitude eox and eta, we can find the power density of that one. So now it will be constant because it is lossless. Now the power will not decrease, but rather it will remain. This density will remain constant at every point in the space for the uniform plane wave. For the spherical and other, there were different scenarios. So here the power density terminates as e to minus 2 alpha z, which I already discussed. So where E and Hy falls off as e to the minus alpha z. Now in the phasor form, now this is an important quantity. Now we will see that it will sometimes it will difficult to remember. We will have alternate expression for these time average Poynting vector. So what we can see that ES, the space, you have EOX, it is minus alpha z, minus j beta z, EX. This is a phasor form of the instantaneous electric field. The phasor form is there. We have no time dependency. Simply what we have, Hs is equal to Ex divided by eta, e to the power minus alpha z, j beta z minus j theta n. Because eta is given by magnitude multiplied with the phase, and this will come in the numerator. So now if you take ES cross HS conjugate, so when you take the conjugate, so all which have the J terms will become the negative of that one, so it will be plus plus. So when you multiply, take the cross product, so these two terms will be multiplied, and we have to the cross product of AX AY, which will give you this will give you the AZ, and when you multiply these two, you will get this expression. So here this will be plus HS conjugate will be e to the power plus j beta z into e to the power plus j theta n. So these two will be cancelled out, and these two will be added. So here what you have, eox square by eta e to minus 2 alpha z e to the power theta n. So if you compute this one and you take the real part of this, so when you take the real part of this, what you will get, real part will be of this will become the you can just take the real part. So it will have the constant. The real part of this will be just the cos theta n. So this is already a real quantity, and this is the complex. So real part of this will be just the cos theta n. So just multiply with the cos theta n will give the real part. So real part of this one will give you the same. So here already we have u x over eta, this one, just we have the cos theta n. So when you take the real part and multiply with the half, you will get the same expression. You can verify. So these two expressions will remain same. So sometimes it is easier to remember this one. Just what you have to do. So you have to take the Schwerer form of electric and magnetic field and compute the ES cross HS conjugate, this cross product. This is a conjugate. You have to remember this because it's a phasor form and phasor form is a complex quantity. If you take the instantaneous form in general in the real world, they are all real. So conjugate will be applied. You can remember easily. So if you want to find the instantaneous, just compute E cross H, because E H are also instantaneous and they are real. So E cross H will give you the instantaneous Poynting vector. Whereas if you take the E and cross H conjugate, so it means they are in the phasor form. Sometimes they write S, sometimes they omit. So you can understand if you have a conjugate here, so it means this we are talking in the phasor form. So this are the phasor forms, and when you take the real part of this one and you multiply here, then it means this will give you the average Poynting vector, average time. This is the instantaneous Poynting vector pz p vector, and this will give you the average time average, this one. These are minor difference, you have to remember both. So this is easier to compute for in general. So this is the expression for the uniform plane wave, whereas you will see that this is the general expression. Both E cross H and this one, they can be applied for any type of EM waves. So this you have to remember in a special case. So now to find the total average power, this is because this is a power, P is the power density. So to find the total average power, time average, we have to integrate over to the whole surface where we want to find this one. So total power crossing a given surface. If you, for example, have an EM wave is moving this direction and you have some surface which is not closed also, and we want to find out what is the total power crossing this surface. So just you compute this integral, this time average Poynting vector dot ds over this surface. So it will give you the total power coming out in this one. Now is this dot ds, so it will be not a vector. This is a here a mistake. So this will be a scalar quantity. Now here it will give you total power here. So here we have an example. We can go through this. In a non-magnetic medium, we have some E equals to 4 cos 2 pi az x. So the wave is propagating in the z direction and the component is the ex. Now we have to find this epsilon r relative permittivity eta, the time average power carried by the wave, the total power crossing 100 centimeters of plane, that is given by defined this. Now this plane is not exactly perpendicular to the direction of propagation. Here I have taken the example which is perpendicular to this is a plane defined by sub z equals to a, and here what you have is 2z plus y. So this is a plane which is inclined to this one, but we have to take the dot product where this plane, this only the part which is perpendicular to the direction of propagation will participate in computing this one. So you have to remember this point in your mind. So as this you have no alpha term, so it will be for the lossless. It will become easier. So alpha is 0 and conductivity is 0. So medium is lossless, beta is 0.8, omega is 2.7, mu is mu naught n. So you can find this V. In general also, if you know the V, if you have, for example, if you know the free space of medium and you know the omega, you can find the beta, which I have given you some question in the test also. So you can use this to find the beta directly. So you can have beta mu omega under root mu epsilon, and you have this, you can find all those things using the expression. You can find the epsilon r here 14.59. Now eta for where you have the lossless medium is just given by mu over epsilon, and mu is same as mu naught where E is as E or E naught. You can find this one. So eta is the 98.7 So intrinsic impedance is 98.7 ohms. Now next is the time average power. Just you have the uh, time average power. You can compute this way. You have this one, and you can go through taking the average of this one, or you can use the formula. So if you go through the formula directly, so in that case, time average cos theta n is 0. So you have e to the power x by 2 eta. So just you can go through this one. So you will have ux power eta, and then you will get the eox square over 2 eta, and you can compute, you will get the time average power. So time average power density is given by 81 milliwatt per meter square. Now on a plane 2z plus yz, so if you want to find the a vector which is perpendicular to this plane, so just you take the gradient. Using gradient formula you can find that. So let compute f is equal to 2z minus y. This is the surface equals to 0. Now if you find out this gradient of this surface, then that vector, because gradient of this scalar quantity will give you some vector, the direction of this vector will be perpendicular to this plane, and if you divide by the magnitude, you will get the that unit vector perpendicular to this plane. So ax is a unit vector which is perpendicular to this plane. So you have some plane, and then you have to take the with this one plane. So this you have ds ax. So ax ds will be uh, this is the unit surface, and ax is this one. This is the surface area, small surface area, differential surface area on this unit plane. So when you put up this one, you will get the here, because we have the dot product. So only dot product, because p average z have direction on the z axis. So only this part will play a role. The 2 by under root 5 will be there as n, and you can compute here. And finally, you will get the total power crossing this plane. Okay. Crossing, and we have to limit this here with the 100 centimeter. In plane is infinite, but we have to limit to the 100 centimeter of its area of this one. So here you can understand the this Poynting vector using this problem. So Poynting vector is very important, and it is used to find the power density associated with the electric and the magnetic fields, or associated with the waves.